Thank you. Good afternoon, everybody. I'm James Baker from the University of Manchester. So from one wonder material to potentially a wonder material of the future. Key word in that is potentially. So I'm going to talk a little bit about what is graphene, what we're doing in the UK, and if you like, some of the case studies in terms of where graphene is starting to play a difference and potentially could play a difference in the future. I'll try and build it into some of the other conversations that have taken place in terms of wearables and electronics and other technologies we've talked today. So where did it all start? 2004, just building on the early analogy, two scientists in the University of Manchester, purely at that time driven by curiosity, took a lump of graphite, the black stuff, a piece of sticky tape, and they peeled that graphite with the sticky tape. They then peeled that sticky tape many, many times. Then under a microscope, they looked through it, and they realized they'd isolated a single atomic layer of carbon. So what is graphene? Graphene is a single atomic layer of carbon. So the analogy from there, it's a bit like taking those big sheets of paper and just peeling one sheet off and had that so-called graphene. So what? What was the interest from 2004? What's all the hype? What's all the talk about following that discovery, that isolation in 2004? Well, having done that isolation, they came up with this list of so-called superlatives. So with respect to my previous speaker, for example, they found as a single atomic layer, graphene is 200 times stronger than steel. It's the most conductive known material. It's flexible, it's transparent, it's bendable, it's a perfect barrier or a membrane which will only allow water to pass through or will stop water from passing through. So a whole list of superlatives came out in the coming years since 2004. Any scientists in the room, any view in terms of what the most exciting feature that came out of that research? Any scientists in the room, the answer is actually the bottom one. Because what they're continuing to find since 2004 is many, many more features for graphene. But now it's not just graphene, there's now a whole family of two-dimensional materials that the scientists are looking at. Again, from a scientific perspective, what does that mean? You're now starting to get people look, if you like, about making artificial man-made materials. Materials that you make bottom up, where you stack two-dimensional materials into a multifunctional material that you don't find in nature. So from an academic viewpoint, there's been a huge explosion in terms of research taking place, not just in Manchester and the UK, but across the world. From my perspective, what's also started to happen since 2004, in particular since 2010, is a number of industrial partners have now started to say, how do I use some or a number of those properties into my product or into my applications? So again, where graphene is particularly interesting is where, for example, you add that mechanical strength into either a steel, a coating, a composite, a polymer, a plastic. Can you improve the mechanical strength? What's even more interesting, if you can actually do that, at the same time also address thermal conductivity, flexibility, etc. So just a couple of case studies that people talk about. One, if you like, is an aircraft of the future. Could I put graphene into the wing of my aircraft, improve the mechanical strength so I can make the wing stronger, lighter, make the aircraft more fuel efficient? You then start getting excited when you look at thermal conductivity. Can I do the de-icing function within the wing, within the graphene, get rid of all the cost, all the weight associated with de-icing an aircraft? You then get into things like lightning strike protection. Anyone who's in the aerospace industry, you have copper mesh within the wing, more cost, more weight. If you can remove that, again, you take out cost, you take out weight, and you continue like that. You're building sensors, you're building stealth. So this multifunctional property is another area that graphene is becoming really interesting. So one of the challenges or the opportunities we have with graphene is that all sectors, all industries are starting now to look at graphene as a potential material of the future. Part of the challenge is how do you focus on what's often called the killer applications that really start to make a difference. So aerospace, I've just touched on there. Other areas that people look at is around mobile technology. So using graphene as a replacement for indium tin oxide, ITO. That's the material currently in many smartphones. It's strong, it's transparent, it's also conductive, so you can make a touch screen. What does graphene do? It does all of those, but it's also flexible, So if you had a graphene phone, because as well, it's a bit like the iPhone 6, you can now fold it up and bend it up and put it in your pocket. You can wear it as a watch. You can actually stitch it into your clothing. Going back to a previous question, there's even people looking at graphene skin, so you can actually wear the graphene wearable within your body. Again, it's an area of potential where graphene can start to play a difference. If you look at the membrane capability, again, huge interest here. You can actually make a graphene membrane, so it'll only allow water molecules to pass through. So as a perfect membrane, imagine a situation we can have a cup of salty water, put a graphene membrane, a little bit of pressure, drinking water would come through. So as a result of some of those great sort of futures, those great innovations, increasingly today you're seeing companies starting to say, how do I use graphene in my products and applications, and how do I bring some of those potential into applications both tomorrow and in the future? So what are we doing in the UK? What are we doing here in Manchester, up in Manchester in the north of England? For me, if I talk about a strategy to take a new product to market, and it's interesting, I mentioned earlier it was first isolated in 2004. Graphene was not invented. Graphene has always been there. Carbon is everywhere, 28% in the body, it's in the air, it's in the ground, it's a naturally occurring material. So while some people would say, and earlier people talk about a new material can take 20, 30 years to take into market, there is an argument that says that actually we understand graphene, we understand carbon, so as well as being 10 years young or 11 years young, I often use the analogy that graphene is actually 11 years old. I actually really understand it quite well, and it's moving incredibly quick. I wouldn't like to call it the Internet of Things, but in terms of materials, from my perspective, I look at carbon fibre as an analogy, 20 plus years before you really started seeing carbon fibre, 30, 35 years before you saw it in mainstream production. Graphene is moving at a different pace to what carbon fibre did probably 25, 35 years ago. So the first part of the strategy, if you're going to take graphene to market, is actually great fundamental science. And at the University of Manchester, I'll just pick on there, a key message there today, we have about 240 now researchers working on graphene research just in the University of Manchester. It's estimated that around the world there are probably tens of thousands of researchers now either working on graphene or using graphene and 2D materials in their research and in their studies. The key message from that is it's moved from physics into very much a multidisciplinary approach. It's in physics, it's in chemical engineering, it's in material science, it's in the biomedical application. So a key message, a key takeaway just in UK, but globally, graphene is very much multidisciplinary. So the first part of your strategy, I call a three-leg strategy, is you need great fundamental science. And when you're dealing at nanotechnology, there's still a lot of fundamental understanding of measurement, material characterization. What's taking place at that nanoscale is still quite a scientific activity. And often when you see presentations on graphene, it very quickly gets into the deep technology dialogue. So the second leg of the strategy in the UK, we've been fortunate to get 2 additional facilities. £61 million, £38 million from the UK government, EPSRC, you heard about them earlier, Engineering Physical Sciences Research Council, £23 million from Europe to build the National Graphene Institute in Manchester. And we've also got £60 million to build the Graphene Engineering Innovation Centre, fondly called the GEEK, which is very much like a catapult that you heard around earlier. So for me, the second leg of the strategy, I call them accelerators, infrastructure, equipment to accelerate that technology through the technology readiness levels, through the valley of death into application. And then the third leg of the strategy is about industrial engagement. So like the previous discussion, how are we going to take product to market? We have some great scientists, some great engineers within the university. We haven't got the applications, the use cases, and the people who really understand what it takes to take a product to market, and that comes from collaboration through industry partners. So the National Graphene Institute up in Manchester, it's a fancy building. It just won the Building of the Year award last night of the Buildings Award, so it's getting accolades for its architecture, for its functionality. For me, what it is, though, is an accelerator. If you're going to take technology from concept through to market, typically, as I mentioned earlier, that takes time. If you can be first to market and do that at cost, affordability, and generate intellectual property, quality intellectual property, then you have an opportunity to start shaping and disrupting in the market. So the National Graphene Institute is in the TRL, Technology Readiness Scale, still is about concepts, still is about fundamental studies. But as well as looking at material, a year ago, the world was obsessed in making graphene. There were a number of companies that spun out to make graphene. You can all go and make graphene at home tonight, get a pencil, get it on a piece of paper, stick your thumb on it, press it many times, or a piece of sellotape. Probably within there, you'll find a few flakes of graphene. You probably won't see it unless you happen to have a powerful microscope in your house, but you can actually make graphene in your own house. The challenge is scaling that up from a few micrograms into kilograms and into tons. But as the last speaker said, you still can't buy quality graphene by the ton, but you can buy reasonable quality graphene. That's good enough by the kilo, by the ton, probably by the end of this year. So the market for the material is moving very quick, and a lot of work is going not just into the material, but into the process stabilization. We're partnered with National Physical Laboratory, for example, in the UK, developing standards, measurements, quality assurance, all things that are absolutely critical if you're going to take a new product or a new material into market. But for me, the exciting bit is not the product of graphene, it's how do you make that graphene into these various applications that create market discrimination, either as a linear disruptor or as a disruptive technology that starts to change the dynamics of the marketplace. The second building, the Geek, is under construction, again in the centre of Manchester. It's very much in the catapult type territory, so it's in the valley of death that we just talked about. Once you've produced that simple scale up, that simple prototype, your one-off dress, you want to make a few hundred, a few thousands, you want to do that repeatably, you want to do it at a yield, at a cost, and the Geek is very much of that in terms of not just the material, but these various applications from membranes to composites, to inks, to fabrics. So again, a key part of the infrastructure being set up and built here in the UK. So in terms of what the university is doing, where the focus is, our focus is really around projects working with industry. We have a number of people who are looking at material supply, measurement, quality standards, but we have a series of companies that are starting to look at these various applications that I talked about. For me, the exciting bit is about building supply chain. When we started several years ago, people were doing bits of this jigsaw. Today, we're starting to build, if you like, top-down collaborations where we have end users, we have material suppliers, we have product suppliers. Bringing that community together to do that in an accelerated way, for me, is where some of the real excitement comes along. So we're working with a number of partners. There are just a few of those. Today, we've got about 55 live projects with 45 different industrial partners. People who know their logos will see everything from aerospace, automotive, energy, paint, inks, composites, steels. So it's a broad range of suppliers from across the supply chain and a number of end users and applications. Just to give you one example of a couple of partners we have in there, a very interesting partnership. We have a company called BGT Materials. That started off being a graphene materials company, making graphene material. Strategic partnership with that company. They were starting to look at thermal management properties of graphene. You heard earlier, it's more conductive than copper, more conductive than aluminium. They actually put a small amount of graphene into an LED light bulb. They found out by doing that, the light bulb was 10% more energy efficient than a conventional LED light bulb, basically because the graphene was dissipating the heat from the light bulb more efficiently than metal. Whilst that was quite interesting, 10% improvement is worth having in terms of energy. The second bit for me is more exciting. They then started to look to re-engineer the LED light bulb product. They're actually now in the process of coming out with about 10 new product lines, from street lighting through to strip lighting, through to lighting products. What they've now found is when they've engineered that solution using graphene, they can now make light bulbs that are up to 50% more efficient than a conventional LED light bulb. A company called Graphene Lighting, have a look at it on the web. You can actually see their products on thermal cameras. you can actually hold the light bulb in your hand because it doesn't get hot. So I don't know if your dresses get hot, but maybe that's an interesting area. Hot from another viewpoint, maybe. But so again, lots of interest from a lighting product type market. Another interesting example is a company called Morgan Advanced Materials. They are a carbon company. They're a company that are into carbon products. They've actually put funding into the university as a collaborative project. They've actually put 2 of their application engineers into the National Graphene Institute. They've put pilot production kit into the institute. They're looking to take some intellectual property for producing graphene that was developed in the lab in the university. They're looking to scale that up into pilot production, but they're looking not to sell the material. They're looking to make that material into 2 or 3 of their product lines, and they're looking to do that in a 2-year window. A conventional model would be saying 3-4 years in university, 3-4 years scaling up. There's potential there to take that from an 8-year program into a 2-year program to be some of the first movers in a few innovative products they're looking to launch in the marketplace over the next few years. So again, just a couple of examples there of what people are starting to do and the different sectors we're trying to work in. And as I say, it's all about the various applications. Just a quick case study that some of you may be aware. So where is graphene? You can buy graphene today. 2-3 years ago, Head launched a graphene tennis racket. It's 99.9% marketing, and it's actually 99.9% graphite. It's trademarked as a Head tennis racket, graphene tennis racket. They've actually put a small amount of graphene into the central section. Technology-wise, it's very basic, it's very simple. The intellectual property they've got is very weak. The trademark they've got is very strong. They've trademarked graphene sporting goods. Engineering-wise, it's subjective. Any sports scientist in the room will know that if you want a tennis racket to improve its performance, the central section's functionality is to stop the racket from breaking. What you really want in a tennis racket is the weight distribution towards the top and bottom of the racket. So a small percentage of graphene has re-engineered the racket to improve the sweet spot of the tennis racket and the performance of the racket. The fact that you have to be Andy Murray or Djokovic to actually prove that is a little bit subjective. You're probably aware that they both use this. More significantly for me, Head sold 250,000 rackets in their first year, $50 premium for the graphene racket. They've now launched 6 different variations of the racket, and they're now into skis and a whole raft of other goods. So quite a bit of branding on that early adopter, but look back in history of new materials, Formula One sports goods often do that. Wearables is a very interesting area. So again, if I look at wearables, we're looking about designing graphene fabrics. Can you actually get the fabric to contain graphene, but then within the fabric it's actually got some of those properties, whether it's conductive, thermal management, battery storage. Again, can't do that today, but today we are printing simple graphene inks onto fabrics to do things like tagging, to do things like simple sensing. If you start combining that with the School of Medicine and wearables, for me, one of the big areas in terms of well-being, just put a bit of graphene into the sole of your shoe. You get lots of information. Any doctors in the room, they're probably all left, but there's a lot of information coming through the feet. If you could project that wirelessly to a simple device on the wrist, in terms of well-being, in terms of detection, different materials in the body, there is actually huge benefits for the well-being healthcare sector if you can start getting that early preventative medicine by integrating the wearables into the body. So where are we today? I promised actually when I first signed up to this to bring a demo, a live demo. So where are we today? Building from the tennis racket. 3 weeks ago, we flew an unmanned vehicle up in Lancashire. So a 3-meter wingspan unmanned vehicle, a drone. Half of its wing was coated in graphene. I would have brought it here today, but I couldn't fit it on the train. Anyone who's got Google, if you Google UAV graphene flight or flight trial, you can see it. It's in partnership with a number of universities and small businesses. We're doing a second one where we're actually taking graphene, putting the graphene into a thermoplastic, and we're 3D printing a number of components for a small rotary wing vehicle. Again, we hope to fly that one within the next few weeks. Partly a bit like the tennis racket, it's about marketing, it's about getting data, it's also about starting to engineer the products into unmanned vehicles, aerospace, because what we really want to do, going back to my aerospace example, is get graphene into the next generation of aircraft. A wing is still probably 5-10 years away, but for example, if I look at thermal conductivity, forget about the wing, the wings are long term because you've got to go through quality, certification, qualification, testing. Fortunately for everyone who flies, they don't put new materials onto an aircraft until it's gone through rigorous testing. But if you actually look at the connectors within the aircraft, there are hundreds of small aluminium connectors doing thermal management, thermal conductivity. If you could take 10 grams out of each of those to several thousand in a large aircraft, that starts translating into tons, which translates into increased range, increased performance. So we're starting to get the attention of the various sectors about how they might use graphene in the future. So just to sum up, for me, this brings together some of the dialogue that you've heard today. TRL, technology readiness level for the technologies, is a scale of maturity. A few people have used TRL today. TRL 1 is blue sky. TRL 9 is a mature technology out there in the marketplace. But as well as TRL, you need to also understand system readiness level or manufacturing readiness level. Graphene is unlikely to be a product on its own. It'll be integrated into a system or a subsystem or a system of systems. So typically technologies go through a fairly linear, slow route up the TRL, and then they get integrated into the marketplace up a mature scale of manufacturing or system readiness level. What we're creating on graphene, for me, which can be a real case study, if you do any sort of case studies on innovation, people often talk about Silicon Valley. I know that was very much around internet, but for me, graphene has got some similarities of that because it isn't a new material, it's an additive to existing materials like steel or composites or fabrics. So typically the universities operate on the right-hand side here. So my left-hand side, the low TRL. What we have with the NGI is starting to extend that TRL, but address some of those manufacturing type issues like process stabilization, standards, application. The geek, when it comes on board, is very much in the valley of death. But what we need through all of that is strong industrial engagement. So for me, as a sort of final statement, graphene's got huge potential. Some of the real big applications are still some years away, where graphene plays a major part in terms of being a disruptive technology, either replacing or doing something very different to the marketplace today. But what you're actually starting to see in the near term is graphene as an additive starting to appear in products like the light bulbs, RFID tags, lubricants, as an additive to a coating, as an additive to a polymer or a composite. It's when we get that engagement and start really understanding the big challenges and what people are trying to achieve that you can actually see some quite big step changes where graphene has got the potential to make a bigger impact going forward. Thank you for listening and happy to answer any questions.